you see here number of elements 2, okay. I value is 0.0031 and 0.15, this is what we had in the problem, 0031 and 0.15, okay. 1.5 I and I, length is 4 into A is 1.25 A in A, number of understand degrees 3, you can see here, understand degrees 3 mark in green, restant degree 6, is it not? So, we entered that. Then the labels are 1, 2, 3 and 4 to 9. Then the labels for the member 1, 4, 1, 6, 2, 8, 3, you can see here 4, 1, 6, 2, 8, 3. Then member 2, 1, 5, 2, 7, 3, 9, 1, 5, 2, 7, 3, 9. We need this for mapping, okay. Done this. Then we want to calculate the fixed end moments. Let us know the beam is loaded with this, okay. Let us mark that figure here. The beam is loaded with a load of 20 kilonewton per meter, is it not, for a span of 4 meters. So, now we know this value is W L square by 12, this is W L square by 12, which will become 20 into 16 by 12, which will be 26.67, is it not, and this is also 26.67, and this loading is going to be 20 into 480. So, this is 40 and 40, and these values are going to be 0 and 0. So, if you look at the degrees of freedom, this is 4 1, 6 2 and 8 3. So, this is actually M 4, this is actually M 1, this is V V 6, okay. This is V 2 and this is H 8 and H 9 and H 3, is it not? Okay. So, I can write the fixed end moments of the member AB as plus 26.67, that is anticlockwise, minus 26.67, okay, plus 40, 0 and 0, and the labels will be obviously 4, 1, 6, 2, 8 and 3. Okay. If you look at span BC, there is no load, therefore, fixed end moment of span BC will be a null vector. So, that is what I entered here 26.67 minus 26.67 40 40 0 0 and FEM2 is 0. Okay. Then we compute the rotational coefficients, then we found the stiffness matrix, the local stiffness matrix, then the complete stiffness matrix by assembling the member and get the complete K. Okay. So, that is what we are trying to get. So, in this we get K local of AB, K local of BC. In this step we get K total, which will be of a 9 by 9 matrix. Okay. Once you get that, you separate KUU, you get KRR, you get KUR and KRU, plug it out and then find K modified. Okay. So, we get KUU, we also get KUU inverse, you can see that here. Okay. We also get KRR, we also get KUR, we also get KRU. Then using this manipulation from the equation, we get completely K modified, which is printed here. Okay. Once I get that, we create a joint load vector. Joint load vector is a reversal of fixed end moments. So, joint load vector will be again a 9 by 1, is it not? That is the joint load vector, which will be reversal of this, which will be plus 26.67, okay, minus 40, 0, minus 26.67, 0, minus 40, then remaining zeros. So, this will correspond to label 1, 2, 3, 4, 5, 6, 7, 8 and 9. You can check that. For example, in label 1 the fixed end moment was minus 26.67. So, here it becomes plus 26.67. Similarly, label 2, for label 2 it was plus 40, here it is minus 40. So, joint load vector is a reversal of fixed end moments. At 3 it was 0, there is no, at 3 it was 0, okay. At 4 it was plus, so at 4 it is minus, at 5 it is 0, okay. At 6 it is plus 40, so 6 it is minus 40, and similarly 7, 8 and 9, 8 0, 7 and 9 are 0, you get 7, 8 and 9 0. So, joint load vector has been obtained here. From this we plug out JLU and JLR. So, this is going to be joint load unrestrained, and this is joint load restrained, and this is going to be 3, because unrestrained degrees of freedom are 3 in this problem. So, we have got JLU and JLR. Okay. So, we have got these two sub matrices from this vector. Then we found the del U matrix or del U vector, then we found the unrestrained displacements, then we found m bar of both the members. So, we get now the final end moments of both member AB and member BC. Okay. Then we ultimately find the RR vector, which is the final result of the problem. Okay. So, we get RR vector, the restrained vector at both the supports. We will see that now. Let us see the output now. Member 1 0.0046, of course, there is a multiplier E here. Okay. This tallies exactly with the matrix what we have here. Okay. 4, 7, 2, 3, 18, can see that 4, 7, 2, 3, 18, etc. Okay. Similarly, member 2 again 6 by 6 with E multiplier. Okay. So, what I do here, we find assembling this a complete stiffness matrix, which is 9 by 9. So, 1, 2, 3, 4, 5, 6, 7, 8 and 9. So, we make a partition at 3, is it not? Okay, we make a partition here. So, if we compare this matrix with the partition, this is unrestrained, restrained, unrestrained, restrained, this is 3 by 3, okay, and this is going to be 6, 3 rows and 6 columns, okay. This is going to be 6 rows and 3 columns, and this is going to be 6 by 6. 6 rows and 6 columns. Okay. So, this can be entertained. Now, from this we plugged out KUU, can see here we have plugged out this matrix, the sub matrix, which is here. Okay. Then found the inverse of that. So, this will have E multiplier. So, this will have 1 by E. Okay. Then we found out KRR, which is this matrix, which is here, is it not, with an E multiplier here. We also found out KUR, which will be this matrix, that is this matrix, which will be here, right, with an E multiplier, and we also found KRU, rth row and uth column, this one, which is this one, which is here. Then we found out the modified stiffness matrix from a simple expression. Modified stiffness matrix is given by KRR minus KRU, KUU inverse, KUR. So, I have all the matrices, KRR I have, okay, KRU I have, KUU inverse I have, and KUR I have. Do the manipulation and get this matrix, which is my modified stiffness matrix for the special element. Okay. The problem does not stop here, I want to solve the problem. So, I got the stiffness matrix modified, then the modified stiffness matrix obtained here, then the joint load vector is taken out, which we already have. We have already understand displacements. Then the RR vector is actually given, RR vector is given by KRU, KUU inverse multiplied by JLU. Okay, this is the matrix of 6 by 3, this is 3 by 3, and this is a vector of 3 by 1 minus JLR, which is 6 by 1. So, compatibility 3 and 3, 3 and 3, 6 by 1, 6 by 1, 6 by 1, which is this vector. Okay. Then we found out the member values for member 1, this is the global end reaction. For member 2, let us plot this. Okay. Let us take this member 1 and member 2. Okay. There is a hinge here, internal hinge here and fixed. So, you know, for member 1, theta 1 is 59.9053 plus, so anti-clockwise 55.9053. Okay. And here it is again positive. So, there is an internal hinge rotation 14.4698. Okay. Then this reaction is 57.5938, then this reaction is 22.4062. These reactions are actually 0. Okay. Then let us come here. So, this had anti-clockwise. So, this is going to be clockwise of 14.4698 and this is going to be again clockwise of 30.3426 and this reaction is negative 22.4062 and this is positive 22.4062. Okay. We can see a very good that there is a perfect compatibility at the internal hinge. Okay. Now, ultimately the end reactions RR are given by this vector, which I am copying back here. Okay. I am copying this vector here. There are 5 values, 6 values, let us do that. So, ultimately look at the problem, I want theta 4, theta 5, delta 6, delta 7, delta 8, delta 9, let us mark them here. So, I want for this member okay. So, I should say m1 okay. I am instead of theta 1 I am calling this n moment m1 or m4 okay. It should be m4 okay. Then m5 okay, m5. Then I should have V6 and V7. Then I should have H8 and H9, correct? H8 and H9. Let us copy this vector back again and write down that. So, let us copy this vector. So, I am copying the RR vector from here 55.9053, okay, minus 30.3426, 57.5938, 22.4062. So, as per the labels, this should be M4, this should be M5, this should be V6, V7, H8 and H9. Let us mark them here. So, this is anticlockwise 55. So, let us mark that. Let us draw the figure. .9053 and this is 30.3426, okay, and this value is 59.5938 and this reaction is 22.4062 and remaining 2 are 0. Let us check, this is going to be exactly same. You can see here 55 and 55. This is 57, okay, 57. So, this is actually 57, this is 57. So, 57, okay, 57. Then clockwise 30.34, clockwise 30.34, upward 22, 22. Okay. Let us take a section and see what is the moment here. Let us say M x, okay, M x should be actually equal to plus 30.3426, okay, minus 22.4062 into 2 meters, because this distance is 2 meters, which gives me exactly 14.4698, which is same as this. So, there is a perfect compatibility of the solution what we have got. We have also solved the problem using substructure technique. So, friends, substructure technique is easy and comfortable to handle special elements and stiffness problems of larger size, I should say that. Okay. We have also seen the computer code used for solving problem with special elements. We have not modified the method, we have used the conventional beam element to solve this. That is the beauty about the whole experiment. So, we have used effectively the computer methods for solving various types of problems varying from 2-dimensional beam element, orthogonal frames, then 2-dimensional truss element, then 2-dimensional beam element with non-orthogonal frames, then 3-dimensional beam element space frame, okay. Then 3-dimensional truss element which we call a space truss, then also 2D special elements. We have also seen the computer codes for solving the above problems, and we have seen the advantage of using stiffness method in solving them. So, friends, with this we conclude the lectures on first module. Hope you have understood all the 30 set of lectures in first module. There are a lot of tutorials available to solve these problems in parallel. Computer programs are also given on the screen. Please play them in your MATLAB and try to solve different varieties of problems, and any doubt arises please post it to us. I will try to help you more in detail. So, the second module and third module are more interesting. We will have some more codes on solving problems with dynamic analysis and fatigue analysis in different modules. So, the whole course is going to be very interesting and more practical experience on writing computer codes for solving complicated problems in offshore structures. Thank you very much and bye.